Thank you very much, Petr. So you can hear me in the back? Okay, good. Before starting the talk, let me just advertise a little bit where I come from. So I work at EPFL, and this is the French acronym for École Polytechnique Fédérale de Lausanne. There are two of these schools in Switzerland. One of them is called ETH Zurich, and the other one is ETH Lausanne, and this means ETH. There's ETH Lausanne, ETH Zurich. And EPFL is the ETH of Lausanne, so it's the biggest school in Switzerland, one part in Zurich, one part in Lausanne. And the one where I work is in Lausanne. Lausanne is somewhere like here, and this is a big lake. Some say it's the biggest in Europe. Lausanne is this city here. Here it's Geneva. This is France. This is France. This is Italy somewhere here. And this is Switzerland. So it's a very nice area with mountains and lakes. And EPFL is always looking for PhD students and postdocs. So if people are interested in doing research there, please consider EPFL. It's not only about the computing and distributed computing, it's all kinds of areas. Okay. So I will talk to you about weight-free computing. Of course, in 3 hours, it's impossible to cover the full space of this crazily big area. So I will give you I will give it a talk from one corner of the area, as you will see, hopefully trying to cover many techniques used to build weight-free algorithms. Sometimes these techniques look simple, but in fact, if you think about them, they are not that simple. And this is a little bit the danger of this field of concurrent computing. Things look a little bit simple because they sometimes mimic the way we humans behave. We concur on something, we distribute the work, but again, behind the scenes, things are slightly more complicated than what they would look like. So get the intuition, but think about it later to see how things work. Feel free to stop me if there is anything. So let me just briefly remind you what Nir and Danny already told you. The world is going towards concurrent and distributed computing. There is almost no application today that is not deployed either on a multiprocessor machine or a network. And in particular, most of the machines today, even very simple ones, they have different processors. Okay, so this is the picture you can get if you go to a talk by architecture people or more system people. As far as, so this is what you get today. So you have these several CPUs, they share the memory, etc. As far as I am concerned, what is important to me is that all these architectures, most of them have two things that are important. On the one hand, processors, on the other hand, memory. Of course, even if the colors are different, the architectures are different, at the end of the day, this is what matters. There are processors and memory, okay? And these processors, they execute your programs, and they do that sometimes by communicating to the shared memory. If you have a large network, the memory is implemented by passing messages. But this is mainly the same picture. So this is another picture of what I just said. You have processors. Sometimes they use some cache. For the sake of this talk, I won't focus on that. And then they, at some point, share memory. So of course, if the processors can do work that is completely independent from each other, then we can hardly talk about a concurrent or a distributed program. If they don't share anything, then we will be talking about different programs. We talk about the same program when they start sharing something. When they start sharing something, they share it through the shared memory. So this is where the difficulty starts, and this is where our job or your job starts, is when they start sharing something, because that's when it becomes complicated. And this is why you need degrees in computer science, precisely because sometimes they share something. So you have a set of processes, they execute each some task, and then at some point they share a memory. When they share the memory, you have to make sure that they don't go to the memory at the same time. Nir already told you that, and Danny already insisted on that. So for example, I will be taking this example a little bit throughout the talk. I don't know whether Nir gave you this example. He usually gives it. Assume you are given as an exercise the following. You have to compute the prime number from 1 to, did he give you this example? You want to compute all prime numbers from 1 to 10 to the 10. And you are given 10 machines. Okay, so, and this was a test to enter Facebook some time ago. You want to enter Facebook, they do this test. They tell you, you have to compute all prime numbers from 1 to 10 to the 10. You are given 10 machines, powerful machines. And you are given an algorithm that, given a number, tells you if this number is prime or not. The algorithm is given to you. This famous algorithm by these Indian guys, which is very efficient, they give you the algorithm. Now what you have to do is make sure you always use the 10 machines, always. They have to be useful. How would you divide the job? How would you do that? Okay, from 1 to 9, it's easy. It starts becoming slightly complicated after 10. And of course, the bigger you get, the more complicated it gets. How would you divide the work? 10 machines that you always have to use. What would you do? So, one. Anybody has a clue? Yes? So what would a job consist of? What does the job do? Yeah, so the first idea is to say, I give this machine all the numbers from 10 to 10 to the 2. And this machine from 10 to the 2 to 10 to the 3. If you do that, what could happen? What's the problem with this approach which would divide the work in advance? So here I split the work. You do from 10 to 100, you do from 100 to 1,000. This machine do, yes? Yes. Exactly. So the problem with this approach is that the machine which will have the numbers from 10 to 10 to the 2 to 100, let's say, is going to finish much, much earlier than the machine that will start from 10 to the 9 to 10 to the 10. The bigger the numbers, the harder it is to compute whether they are prime or not. Okay? So this approach is not good because most of the machine will finish and then one machine will keep working. And this is not what we want. You won't be able to enter Facebook if you answer this. So what should you answer? Raise your hands. Okay, yeah? Exactly. So the solution is you have to tell the machines, compete on the numbers. They have to compete on the numbers. A machine starts for, let's say, number 11, say, oh, it's prime, comes back to the shared memory and says, give me the next free number. Number 12, okay, it's not prime. Come back, give me the next free number. How do you implement this idea of give me the next free number? You need a shared object. If we don't use any shared object and we divide the job in advance, the solution is bad. So we have to have them come and compete for the number. This competition is achieved by a counter. The counter will tell machine 1, the next free number is 225. And then a new machine is done, comes and says the next free number is 226, etc. Do you see the solution? The solution, however, is based on the fact that we have a counter. The job of the counter somehow is to distribute the work. Notice that the counter is just a passive object. It's just sitting there saying, this is the free number, but it's the master of the computation. The master of the computation is this shared object, the counter. Now, how do we implement a counter? If we have a sequential program, we write something like this. Counter is a class, initialized to 0, and it has an operation, get and increment, and the core of the operation consists simply in incrementing the value. Is this clear? If this is not clear for you, then you have problems. So this is clear. Okay, so this is in the sequential world, very easy. Now, you take this counter, you use it for the problem I'm talking about, it's not going to work. Why? Nir told you, because you can have race conditions, right? So what should you do to protect this counter? As synchronized, very good. More specifically, you have to make sure that these processes that are accessing the counters, they obey some discipline. Okay, they lock the counter. So you add synchronized means there will be a lock on the counter such that when machine 1 comes and says, give me the next number, it first locks the counter, increments, gets the next number, go back. What is the problem with this solution based on using the locks? Any intuition? Okay, contention. You can have two machines, they both finish their job, they come, they want to access the counter. But is that a problem? One of them will grab the lock, increment, get the number, and the next one will grab the lock, increment, get the counter, the next counter. Is that a problem? Why? Raise your hand, okay? Okay, so now assume the guys of Facebook, they have so many applicants. They make the problem slightly more difficult. They tell you not only you have 10 machines, but these machines are not completely reliable. Sometimes some of the machines can fail. Of course, the notion of failure can simply mean that some of the machines can take a nap. Take a nap in operating systems means they can be swapped out. They can just be asynchronous. They can slow down for a while. So what if they tell you some of these machines can fail? Fail is just a picture. What's the problem then with the solution we just discussed using locks? What could happen? Something bad could happen. I'm sure Danny told you this. Yes? Say it higher. Yeah, so the other threads, what could happen is, say machine 3 comes, finishes number 225 and says, give me the next number, execute synchronized, meaning gets a lock, and this machine immediately fails after getting the lock. Again, failing might simply mean that the machine is, the processor is swapped out by the operating system, doesn't give it priority, etc. So for all the duration where this processor is failing, is taking a nap, nobody is progressing. Is that clear? Which means, again, that we are not making use of all the machines. So this is not a good solution. So far, so good? So this is not really... Of course, if you use locks in a smart way, what you basically do is that you reduce this time during which a machine is holding the lock. Okay? Lock algorithms that are smart, this is what they do. And this is what Nir Shavit told you about, reducing this window. So all these algorithms using test and set, compare and swap, etc., they try to be smart in keeping the lock. So locking is difficult, first because, as you have seen from Nir Shavit's book, if you want to reduce the window during which you take the lock, then you start trying to become smart. When you start trying to become smart, you usually make mistakes. Being smart and making mistakes usually go together. If you never want to make a mistake, you don't really become smart. So they go together. So if you want to become smart with taking locks, you make mistakes. And this is what happens in practice. You have a lot of mistakes. And as I just pointed out, at some point, somebody has to take a lock, and this makes the whole process fragile, because if a machine still fails, then you have a problem. Just to make this notion of failure concrete. So here to motivate the need or the problem, I told you some machines might fail. In concurrent computing, it's very rare that machines fail. However, as I just said, it's like taking a nap. And concretely, some numbers from Maurice and Nir's book, a cache miss, when a processor misses its cache, it delays the process by 10 instructions. If it's a fault that is missed, it's few millions. It's an OS preemption, it's hundreds of millions. So what I'm saying here is that it is not that some processors will fail, it's that they will be delayed for 100 million instructions. So what is the difference between somebody dying and somebody disappearing for 100 million years? At the end of the day, it's the same, right? So this is why we call that failure. So hence comes a completely different field of research, which is, are there alternatives to locking? Now I'm back to where Danny Handler, I guess, motivated the talk. We have to think about something else. Now, in practice, what people do today, what they should do is still not clear. Some people say you have to do locking, but be very smart. Some people say you have to avoid locking at all. So there are the two schools. So here we're not taking any positions. Nir presented to you the locking. Danny presented to you a solution without locking, and I will go one step further, as you will see. The talk that Danny Handler gave you is to say, how can we build data structures like a counter without locking? But notice that without locking means that nobody is allowed to use locks. Okay? It doesn't mean that all the machines, if I go back to the example of computing prime numbers, it doesn't guarantee to you that all the machines will be able to work, will be able to get a number. It simply means we don't use locks. So we might have a solution where we don't use locks, and still some of the machines, let's say half of them, are able to get the number, and half of the machines are not. It is still a lock-free solution. The ideal world is called weight-free. The ideal world means every machine, every processor that invokes an operation eventually returns from that invocation. If I go back to the example of the machines with the counter, this means all the machines are able, when they want it, when they invoke increment, should get back a reply. Each one of them. Okay? It's called weight-free. Of course, you cannot guarantee weight-free if you are using locks. But not only you should not use locks, but you have to be even more sophisticated to guarantee some sort of fairness. So this is like some sort of fairness. Everybody has a chance to have a counter. Okay? So it's like a socialist regime where everyone has a chance to have a counter, at least once. Okay? Whenever they invoke. Of course, if you allow processors to do this, then you have problems because it's not clear how they will leave the state of the counter. If you just let them all go to the counter to achieve this, you have a problem. So we need still to ensure that the counter behaves like a counter. And this is called atomicity. And this is also something that Danny told you about. I won't go into much of the details of atomicity, but just a couple of reminders. The best way to understand atomicity is to tell yourself, this is like acquiring a lock, but without having the locks. Atomicity is exactly just acquiring. By the way, atomicity is also sometimes called linearizability. The word linearizability came from Maurice Herlihy and Janet Wing. You are going to see Maurice tomorrow. And Maurice Herlihy got the name from Leslie Lamport, who used to use the name atomicity. So sometimes you see atomicity or linearizability is the same thing. In concurrent computing, is the same. Atomicity says, informally, everything happens as if you grab the lock. Execute the operation, release the lock. Okay? But you don't have locks, because otherwise you won't guarantee weight freedom. So you have to give that illusion without having the lock. This is atomicity. And more specifically, atomicity says every operation appears to execute at some point in time as if the object was locked. So far, so good? Okay. So in short, a big challenge in concurrent and distributed computing, sometimes people say concurrent to mean shared memory and distribute to mean that you have geographically distant machines, but at the end of the day, it's the same. A fundamental problem in concurrent and distributed computing is how to weight-free implement atomic object like a counter out of the objects that are provided in hardware. So this is a big challenge in computing. I will just give you, hopefully, an overall idea, but from one angle of this question. So the model I'm going to be using to explain to you this big challenge, why is this challenging? We have a finite set, we call them processors. The machines in the example of prime numbers, the processors, etc., I call processors. Okay? They are denoted P1, P2, Pn. So which means they have unique identities, and they know the identities of each other. So this assumption is extremely important. Sometimes people tend to forget it, because you have some applications, more and more today, where privacy is a big concern, where processes do not want to share their identities. So let me just give you a quick example. Go back to the counter example, but now assume that the goal is not to compute prime numbers. You created a website and you are renting videos. And people can rent videos from your website, some kind of Netflix, new generation. So people rent videos, and whenever they rent a video, they increment the counter. Why? Because you want to remember how many videos of this kind have been rented, right? So you have to implement the counter. Good. But now, maybe people, your customers, maybe they don't want to reveal their identities. So for some movies about animals or nature or science, I don't mind. I want my name to be there. I want people to know that I have rented this fantastic BBC movie about Einstein. But there are other movies where you don't want to leave your name. And this is exactly what happens today. People don't, so if you don't want to leave your name, the problem of implementing a weight-free object is much, much more complicated. I'm not going to address that, but keep that in mind. If processes are anonymous, then the challenge is much, much more difficult. The whole game changes. So the assumption that all processes have the same identities is very important, makes a difference. If you are interested in the case of anonymity, you can do a PhD on that. It's an interesting problem. There are already some results, but the field is still open. We assume that indeed the system is concurrent. Processes, they compete, so to speak, but each of them is sequential. Okay? Each process is sequential. So again, this assumption does not always hold. If it doesn't hold, the whole game changes. This field of concurrent and distributed computing, every single assumption makes a huge difference. Okay? So the difference between a paper in so-called the theory of distributed computing and the paper in the system is that here the assumptions are clear. Okay? So try to be slightly theoretical and make sure your assumptions are clear. Processes know each other. Every process is sequential. Third assumption. Unless explicitly stated otherwise, which is not going to be the case here, we assume that the speed of processes is unknown. We don't know how long it will take them to execute any operation. This assumption basically means that I don't know whether a process is going to be fast or take a nap of one instruction or 10 or 10,000. I don't know. So this picture is going to come back over and over, and this is a program. Execution of a program is this. 3 processes executing. And again, for the sake of this talk, I'm going to assume that not only processes are sequential, they take naps, and the only thing they can do is take naps. They cannot start behaving arbitrarily. A process compute the prime number, comes, say, give me the next. Okay? It cannot start doing things it was not supposed to do. Okay? In other words, I'm not going to assume what is sometimes called Byzantine failures or malicious failures. Have you heard of Byzantine failures? Who has? Okay. So Byzantine failures means the process is malicious. Think of it as somebody has put a machine that doesn't want to play the game of prime numbers. It just wants to destroy your entire program. Sometimes it's not do it on purpose. Sometimes it's just a bug that is provoking this. But that's how you model it. Here, I'm excluding that because that creates more problems and I don't have time to cover that. But this is another source of interesting research, by the way. And a process that executes the computation correctly without crashing is called correct. We are going to assume that the processes, they execute some local computation. In our example, the local computation is this number prime or not? This is a local computation. I have the algorithm, I execute it on the number. Or they access shared object. Accessing the shared object is going to the counter and say, give me the next free one. So this is an important picture, which basically depicts the fact that the processes they execute, these are local operations, and sometimes they invoke a shared object operation. This picture is important because it really says that there is nothing instantaneous. You want to give the illusion that this operation happens at one point in time. In reality, they don't, of course. But the whole game is to give this impression. So remember, this is what Danny said, the game is to guarantee that every operation appears to execute at some point in time. Usually, when you try to argue that an operation, an object is atomic, you want to argue that all its operations, whenever they are invoked, they appear to execute at some point in time. This point in time is sometimes called the linearization point. Okay? So if you are asked to implement an object that is atomic, weight-free, and we ask you, prove that it is atomic or linearizable, proving that means you have to argue that every operation that executes has a linearization point. What does that mean? It means an indivisible point in time. This is an abstract notion. An indivisible point in time according to which it could have been executed. Okay? And this point in time has to be somewhere here. I will give you concrete examples. And you want to guarantee atomicity together with this ideal property. Any correct process means somebody who doesn't stop, doesn't fail, that invokes an operation, increment, eventually, gets a reply. Eventually means there is a time after which it does get a reply. Okay, the word eventually is sometimes confusing because in certain languages like in French, éventuellement means maybe. Eventually, in English, means it will get a number. It's not éventuellement, it will. Okay. So the notion of weight freedom is very important. Before I dive into it, let me just emphasize. It's very important because it says something about the robustness of your object implementation. Because weight-free means every process, no matter what happens to the other processes, is going to access the shared object. It's going to obtain a reply. If I go back to my prime number example, this means even if 9 machines fail, the other machine, the last one, will be able to continue working. Okay? This you get because of weight freedom. You see what I'm saying? Any machine, no matter what happens to the others, is able to execute the operation. So let me now give you a concrete example that I will be using a lot this morning. I'm going to take the simple object I know of, which is the register object. Did Nir or Danny told you about this register object? Okay, so this is the simplest object you can imagine. It's an object with 2 operations, read and write, just a file. It's an abstraction of a file. This object, you can read what it contains and write what you want it to contain. If I have a register or a file object in the sequential world, what do I expect from it? How does it behave? Usually in a file, when I write something, I go home, I come back, I read, I find what I have written. If it's sequential, if there's only me accessing the file or the register, I write number 1, I go home, I come back, I read, I find number 1, if I'm alone. Okay? That's the behavior of the register. So it has 2 operations, and here, for the sake of simplicity, I assume that this integer contains only, this register contains only integers. But whatever I'm going to say holds for whatever you want. The integer is x. And what we call the behavior of the object in the sequential world is this. When I read, I return value x, what the register contains. When I write value v, I put v in x. I return OK. Is this clear? If this is not clear again, you have a problem, not me. Okay, good. So this is the reference point. There is something you have to understand really. All this game of concurrent and distributed computing is defined relative to what happens in the sequential world. Now, I'm going to talk to you about what does it mean to be atomic for a register. The definition of atomic is with respect to this. This is the reference point. We assume that the sequential world is easy and clear, and we define concurrency and distribution with respect to what we know. This is like the pillar, the behavior of the register, okay? This is how it behaves if there is no concurrency. This we know. It's like, just like the counter. We know how it behaves in the absence of concurrency. And we ask ourselves, now, if I'm having a register that we can read and write in a concurrent world, what is an atomic implementation of it, okay? When can I say that an execution is atomic? So let's look here and remember what I said. An implementation, an object is atomic if every operation appears to execute at a single point in time. Remember, appears, what does it mean, appear? The only way you observe a register is by invoking something on it and looking at the reply. That's how you see it. Is this execution atomic? Raise your hand, those who believe it is. Okay. Who believes it is not? Can you argue why it is not? The word we call write too long. Okay, good observation. So here we are assuming that we are only writing integers. So it's very short. We don't have this problem of buffer overflow or whatever. And this execution, with this assumption that we are only writing integers, is indeed atomic. How do I argue that it is atomic? By exhibiting linearization point. I can say everything happens as if this operation execute at this. Okay, these guys are big, but they're supposed to just to be visible. They mean instant point in time. This executes here, this executes here, this executes here. I found a linearization, a set of linearization points, therefore this is atomic. You have to notice something important. All this argument is based on the fact that I know that a register in the sequential world behaves such that the read returns the last value written. If it was a different object, maybe my reasoning would be different, okay? What about this one? Atomic? Raise your hand. Good. We can go quickly. What about this one? Okay, so here the argument is slightly different. Proving that something is atomic means I need to find the linearization point. Proving that something is not atomic, I need to prove that there cannot be any linearization point. Okay? It's not saying, oh, this sequence doesn't work. No. I need to argue that no, linearization is possible. How can I argue this? I can say, okay, assume this is linearizable. This is atomic. This means I should find the linearization point here. Let me put it here, wherever I put it, here. This guy, I could maybe linearize it here before this one, because it returns 0. But this one, I have to linearize it here. And no matter where I put the operation, this operation has to return 1. Has to return 1 because this is what I expect from the register. Therefore, impossible because it returns 0. Okay? So now I assume that you are able to prove that things are linearizable and prove that they're not. With this very simple kind of reasoning. The kind of reasoning involves two things. You have to put the linearization points within this space, and then you have to argue about the correctness of the register in the sequential world. Okay? Is it clear what I'm saying? Good. Just to give you a slight different perspective, assume now we are not talking about registers. We are talking about queues. I think Danny told you about queues, right? He did. So queues, the semantics is different. You enqueue, you dequeue. When you write, you don't erase what was there. So it's different. And this is what you could expect to be a simple semantics of the queue. If there is nothing in the queue, you return nil when you want to dequeue. If there is something, you remove the first element in the tail, etc. I just want to make sure you understand. Is this atomic? Good. So again, because I can find linearization point, and here I will argue because I know the semantics of the queue. Okay, good.